Hello, everyone. This is the lecture for section 3.7 for the Math 210S portion of our course, Rational Functions. So what we're going to do in this section is we are going to define a certain group of functions, right? And it's going to help us in being able to write down and sort of formalize some of the language that we're going to be using in calculus. Okay, so this section, it's only one section, but it's going to be a two-parter. I'm doing two things here. I'm showing you a set of functions that we're going to be playing around with, right? And we're going to start getting comfortable with notation for calculus. Okay. So first of all, what I want to do is define what a rational function is. A rational function is anything that has a polynomial on the top and bottom of a fraction. Okay. This is, this is a rational function. Okay. So I've got a collection here. 1, 2, 3. Okay. So if you can see, right, this one, that one is one of the run-of-the-mill polynomials that you'll encounter, right? Notice at the top and the bottom are polynomials, right? This one also counts. 3 is just a number. However, it is a polynomial, right? It just doesn't have all the stuff up in front of it, okay? And the x plus 6, obviously, that's polynomial, right? The last one is, that one doesn't work. This is the thing that screws it up. We're going to get to these. This is an exponential function that I circled, right? We're going to get to them. Not yet, though, right? But this is the thing that screws it up for h, okay? That because that's not a polynomial, right? That whole entire thing is not a rational function, okay? Okay, so now, what tends to happen, what we need to do is, if you ever go ahead and put these into a graphing utility of some sort, Desmos, your graphing calculator, right? They're going to produce graphs, right? And they are really wild, okay? And what we need is a way to write down, to describe said behaviors, right? And that's why in math we have this thing called arrow notation, okay? This is the language that we're going to start being able, this is the sort of like the notation that we're going to be writing down, right? It's very shorthand for a whole bunch of other stuff, okay? So there's 7 of them on the left-hand side of your screen, right? And I'm going to write the meanings of them. And then we'll see how we use this notation to describe these kind of graphs, okay? All right, so the first one that I'm going to do is this one, okay? X, right arrow, A, but notice, right, it's got this negative right there, and it's in an exponent, right? So keep that in mind, right? So first of all, let me write it out. I'm going to say it out first, and then I'm going to write it, okay? What that means is as your x values approach a value x equal a from the negative side, okay? So let me write it out, right? As your x values from the negative side, okay? So, and I'm going to put a dot, 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 because this one tends to have some stuff on the tail end there. And we'll get to that when we see calculus, okay? But what we're doing here with this one, right, is we are approaching an x value, right? The x value that we're approaching in this case is a, right? A can be whatever it wants. But we're approaching it from the negative side, right? Or from the left side, since the left side tends to have the negative values, okay? So hopefully you guys see you see what's coming up, right? What's this thing mean, right? It means the exact same thing as your x values approach x equal a from the positive side. So for this one, right, x equal a from the positive, we are approaching from the positive side. Another way that we tend to say it is we're approaching it from the right side, since the right side has all the positives, right? Okay. Next one. Hopefully this is making sense. You guys see how this nomenclature is sort of working out, right? So this one, x right arrow infinity, right? Okay, this says as your x values get infinitely large, positive. Okay, so let me write it first before I explain it. U-E-S get infinitely large, positive. Okay, when we say this, when we write down this over here, right, we are essentially saying that we are letting our x value get positive and really big. Okay, think of, you know, a million, a billion, a gajillion. We're saying that. Okay, but they all have to be positive. Hence, we're saying going toward the positive, right? Positive infinity. Okay, same thing for the other one, right? Let me highlight the next one down. Come on, there we go. Okay, well, you guys see how this is working? Gets infinitely large. This one is negative, right? Okay, so notice, right, between these two, this one and this one, right, they're getting infinitely large, right? But the difference is one of them is going toward the positive large numbers and the other is going toward the negative large numbers. Okay? All right. We're getting there. Okay? Okay. Next two. Hopefully you guys, I mean, remember how I said, right? Mathematicians are lazy, right? This is how they do it. This is the notation that they use. Okay? Okay. So we know from a couple of chapters ago, right, that this is equal to y. Whenever we say f of x, we're referring to y values, right? Okay, so then let me go ahead and do that first one, this one in particular, right? The one that I left highlighted, right? This is saying, right? Y equal f of x values in E large, G, E positive. Okay, so the first one, the one that I left highlighted, right? That is saying that we're letting our y or our f of x values, right? They're becoming infinitely large positive values. Okay? Okay? Next one means exactly the same thing, but basically what we're doing here, right, is interchanging sort of like the meanings and the arrows and the f of x and the x's and the positive and negative infinities, right? But they all sort of, you only need a couple of them to make sense of it all, okay? The next one down, this one right here, this one saying that we're letting our f of x values or our y values go to negative infinity. So they are becoming infinitely large negative values. Okay. Okay. And then the last one, right? The last one is saying that your f of x values or your y values are getting closer to a y value equal to a. Right? So let me write it down now. Whoops, values. Okay. In this case, we're saying that our y values or our f of x values are getting closer to a specific value y equal a. Okay. So why? Why have this? Okay. It's for graphs like these. Okay. This right here, this function, okay, this function has this graph. Okay. And it looks a little wild. Okay. Notice that it has this line right here, and it has this one that goes right across here, right? So I'm going to write them in. So this line is x equal positive 2. And this line, all right? Okay, so hopefully you guys remember from our very first section, right, that there are certain things we can't plug into certain functions, right? If you take a look at this function right here, if you take a look at the function that we have graphed, that one, right, there's a number we can't plug in. In particular, right, there's a number that's going to make us divide by 0. That number that divides by 0 is positive 2. And lo and behold, look at where one of those lines are. Okay? Okay. Hopefully, sort of like the math is sort of, the math puzzle pieces are meshing in there, right? Okay. Now, this is going to be the very first section where we're going to do this. We're going to be describing end behavior and describing local behavior, okay? So I'm going to split those up. This is going to be end behavior, right? And over here, I'm going to do local. OR, there we go, okay? Okay, so when we talk about end behavior, right? You guys see this graph? The graph is actually this blue line right here. Actually, let me make it nice and thick for everybody to see, right? This is the actual graph, this blue line that's right here, right? The one that goes in both of those directions like that, okay? When we discuss end behavior, okay, we are looking at this. We don't care about really when we're close to the origin of a graph, right? We care about what happens when we take this like super, super far, way over that way, okay? And we want to know what our function is doing, okay? And likewise, right, if we take it to the other end, this way, whoosh, right, we want to be able to describe what our function is doing over there as well, okay? In this case, right, our function is doing the same thing on both directions, right? So when, let me erase that. So in those two directions, we have this going on, right? So let me write down what we're doing. We are trying to find when x tends to positive infinity and when x tends to negative infinity. We want to determine what happens there, right? As our x values go way over to the right and way over to the left, okay? And in this case, right, my f of x values, right, they tend to a specific value 4. Both of them do. Okay, so if you take a look, right, you guys see that, let me actually make this, you guys see hopefully that there's a dotted line that goes across, right? So that's something that I'm about to cover, right? But the graph that we have approaches but doesn't cross it. It just keeps going. It gets closer and closer and closer and closer. It never actually crosses, right? And then likewise, on the other side, it does the exact same thing. It goes whoosh all the way that way, right? It gets closer and closer, but it never crosses, right? So what happens is we say that as x approaches positive infinity, right, our f of x values tend to 4, right? They tend to head toward y equal 4. We are describing this portion of the graph, that, and as it goes this way, right? Okay, that is that first line. Come on, there we go. This portion, as this goes that way, and we keep going that way, right? That is the second portion of our explanation there. Okay, there we go. Okay, that is us describing the end behavior of this function. Okay. Okay, local behavior. This is the one where we're looking sort of relatively, we are looking at what's happening close to the origin, close to 0, 0. Okay, now, you see that line right there, right? That is one of our local behaviors that we want to describe. Okay, so this is where it gets a little funky, right? So what we want to do is this: x right arrow 2 from the positive, x right arrow 2 from the negative. So we have two ends here that we need to describe, right? So the first one is saying what's happening when our x approaches 2 from the positive side. We are doing this. We are trying to get closer and closer to x equal 2 on the graph. On the graph, right? So we are trying to find out what's happening here. So look at what's happening. It's shooting straight upward, right? Okay. So when we do this, right, we say our f of x values are tending toward positive infinity. Since the y values, as we get closer from the positive side, right, our y values are blowing up. They are becoming bigger and bigger and bigger, right? So this is how we describe that local behavior. On the other end, right, look at what's happening. Our graph is doing this as we come at it from the negative end, right? So for this one, we would say f of x is tending toward negative infinity. Okay, that's it. We are describing the local behavior and the end behavior of this function right here. Okay. Okay, so let me move on. Actually, before we move on, you guys remember that there was the red line that's right here. You guys see that red line, right? And then we had that green line that went across, right? They actually have specific names. Okay, we call those they're boundary lines, right? But the way the name that we give them is asymptotes. They're essentially lines that are functions. They may cross, but at one point they just get really, really close, never cross it. Does that make sense? Okay. Okay. Next example. Okay. For this one, I'm not giving you the equation for this one, right? I'm not giving you the equation, but we'll figure it out in a second. Yeah. What I really want to do is this, right? The horizontal and vertical asymptotes, and then give me local and end behavior. Okay. So hopefully you guys see, right? Y is equal to positive 3. And then here, x is equal to negative 2. Okay. So let's first describe local and then behavior, right? Okay. So let's do the end behavior first. That's the one that goes, x goes to infinite and x goes to negative infinite, right? Okay. I'm just going to write these out so I can just fill them in after that, right? Okay. Hopefully you guys see, right? This end, as it just keeps going that way. And it gets closer and closer to y equal 3, right? 3. And then it does the same thing on the other end as well. Okay. So we're saying here, right? What we're saying here is as x gets really big, either positive or negative infinity, right? My y values are getting closer to y equal 3. Done. You guys see how, remember, right? Mathematicians are lazy, right? They do it in their notation. This right here is that notation. Okay? Okay. Local behavior. This is the one where we want to handle this line right here, this one. Right? We know what that line is. That is x equal negative 2. So to start with, right? We want to find when x approaches -2 from the positive side, and x approaches -2 from the negative side. Okay, and now we get to describe what our f of x values head toward, right? Okay, if we took a look at the first line, right, as x approaches -2 from the positive side, we want to see what happens if we do this, right, on our graph. And if you notice, it's making us skyrocket, right? Okay, so that automatically tells us that my f of x values are going to positive infinity, right? On the other hand, right, if we go at it from the negative side, we're taking a nosedive. So then this is saying my f of x values are heading toward negative infinity. And we are done. All described. All done, all done. Okay? Now, remember I said I wanted to figure out the equation for this graph, correct? Okay? A little quick method for how to graph one of these, right? The function here, right, is going to be this. F of x is equal to 1 over x plus 2 plus 3. This right here, this function, is the graph that's on the left. Okay, and excuse me. Hopefully you guys see how I picked that out, right? The plus 3 came from here, from this line, right? The horizontal asymptote. And then the plus 2 came from here, where the vertical asymptote was going to be. And it's opposite, right? You guys see that? Cool. All right. Hopefully you guys are getting the hang of how to write, how to describe local and end behavior for graphs like these, right? Okay. Moving right along. So now I'm giving you guys a function. I'm giving you this one, right? I want to sketch it first, and then we're going to describe the behavior. Okay. So we know this is going to give us the horizontal one, right? And this is going to give us the vertical one. So our vertical asymptote is going to be at -1, so I'm going to draw that in. And our horizontal asymptote is going to be at -2, so -2 right here. And at this point, I'm going to just go ahead and slap the rest in. We know that one piece is going to be down there, and the other piece is going to go like this. Okay? As always, you can grab the function and throw it into Desmos just to make sure. Okay? All right. But now, let's list all the stuff out, right? So our horizontal asymptote, right? We know that's going to be y is equal to -2. Vertical asymptote, because we already drew them in, right? X is equal to -1. Okay, now let's do the end behavior. Okay, local and end behavior. Local behavior, end behavior. All right. Let's do the end behavior first, since that one seems to be easy, right? So as x goes to infinity from the positive, whoops, positive infinity. What am I doing? What am I doing? Come on, come on. Positive infinity, x approaches negative infinity. Okay, and we want to know what my f of x values are tending toward, right? Okay. If we go x going positive, right? That's the one that's going all the way this way. We want to know what's happening as we keep on going that way, right? Hopefully you guys see that is going to be -2, right? And the same thing for the other one, -2. So for our graph, both ends are going toward 2 as x goes to positive and negative infinity. Okay? Okay. For local behavior, we know, we see this, right? That's the vertical asymptote. So we get to describe what happens at the vertical asymptote. So we need an x approaches -1 from the positive side, and x approaches -1 from the negative side, right? And we want to look at what happens to my f of x values. Okay? As f of x goes, as x values go to -1 from the positive side, we are doing this, right? We're looking at what happens when this happens, and notice, look. It's skyrocketing, right? So since it's shooting straight up, almost, right, we can go ahead and say that our f of x values are going to positive infinity, okay? On the other hand, right, if we go to -1 from the negative side, we can see that those y values are going to negative infinity. Done. Okay? All right. So hopefully you guys see, first of all, right, how and where I'm getting the horizontal asymptotes, how I'm getting and where the vertical asymptotes are showing up, and then how to describe the local and behavior of, we're using rational functions in particular, right, to demonstrate the nomenclature, how to write this down, right? But this language, this arrow notation that I was just covering, all of this, right, is common throughout calculus. We can use this kind of language, we can use this kind of notation for any function now, okay? And we'll see that when we start covering the actual calculus-y portions, okay? Okay. So there is something I need to cover, okay? And that is the domains of rational functions. Turns out some stuff happens sometimes, right, that we need to keep an eye out for, okay? So first of all, since rational functions have denominators, and we know that if we have a fraction of some sort, right, we can't divide by 0, right? We cannot divide by 0. So to keep us from dividing by 0, right, we have to set the denominator, right? Whoa, I needed the black pen. We set the denominator equal to 0 to find domains. We did this first section of the class, right? But there's some funky things that happen, right? And this is what I wanted to show you guys. Let's take that function right there, okay? The graph is over here on the right, okay? Now, hopefully you guys see there is a vertical asymptote right there, right? And there's a horizontal asymptote, okay? But what I want to do now is this. I'm going to factor this, x plus 3 over x plus 3, x minus 3. So what I'm saying is that bottom, this right here, all of this is actually equal to that. Try it, FOIL it, you'll see I'm right, okay? So what the heck happened, right? So first of all, let me explain what we should be looking at, right? Okay. This one, the x minus 3, right? Whoa, undo. The x minus 3, this one, right? That's here. But if you remember from section 1, right, our very first day when we started covering this stuff, this one should have an asymptote too. Whoa. I guess I shouldn't circle stuff, at least not heavy. This one should have an asymptote as well, right? But that one's not there. And what I want to point out is this. Whoa. You guys see that thing right there? So what is essentially happening here is this. I'm going to actually highlight it a little bit. The graph keeps going that way and then keeps going this way, right? All the way downward, right? But then it skips a value. It just jumps, okay? Got it? Okay. This right here is what we call a removable discontinuity. The short pre-calculusy word that we like to use is we have a hole. Okay. Now, let's go back to our function, this one, right? Notice this. We have an x plus 3 on top and an x plus 3 on the bottom. Those cancel. Whoa, whoa. Come on. Right? That cancels that. And all we get left with is this. 1 over x minus 3. This right here is this graph right here. Right? However, because we had that x plus 3 cancel away, it got left with a hole, right? So, to answer this question, find the domain. Okay? We're getting closer. The domain for this function, negative infinity to negative 3, union. Negative 3 to 3, union 3 to infinity. Because of our function itself, the original one, right? We couldn't plug in positive 3 or negative 3, right? It just so happens that positive 3, the x plus 3, right? That one canceled away. That one produced a hole. Okay, the other one got left behind as an asymptote. That is the negative 3, this one. Got it? Okay, we're getting closer. We're getting closer. We are noticing stuff, right, that we're going to be seeing a lot of in calculus itself, right? So that dot, right, that was what we call a removable discontinuity. Or, for short, a hole, okay? Okay, we're getting there, okay? Quick check. Try these out, okay? Give me the vertical asymptotes. Give me which ones are removable discontinuities, and try to describe the graph, okay? For these, right, you might need to factor to determine whether or not you do have a removable discontinuity, whether you do or you don't have a hole, right? So get to practicing that factoring, right? Okay. We'll cover these in class. Faux show. Okay. Now, horizontal asymptotes. Those are sometimes a little harder to determine for general rational functions, and that's what I'm going to cover here. Okay, and in particular, I'm just going to cover a handful of them. I'm not going to cover a large swath of them, right? But for the most part, these couple of rules, right? These couple of rules, you could take these to the bank. They tend to work regardless of how big the top or the bottom are. Okay, so what we are going to be looking at in particular is the degrees of the top and the bottom, right? We're going to be looking at the degrees of the polynomials on the top and the degree of the polynomial on the bottom, okay? And we're going to be comparing those two degrees, okay? Those are the only three that I'm going to be covering. And the three that I'm going to sort of spell out is this: when the degree of the top is bigger, bigger, right? When the degree of the top is equal, and then when the degree of the top is smaller. Okay? Okay. So the first one, the degree of the top is bigger than the degree of the bottom, right? We have uh, a, whoops, I put them in the wrong order. I wanted to explain these in a particular order. When the degree of the top is less than, when the degree of the top is equal, and then when the degree of the top is bigger by 1. Okay, I'll cover that in a second. Okay, let me cover the first one. Suppose the degree of the top is smaller than the degree of the bottom. So you have something that looks like this, right? You have an x to the 7th plus stuff divided by an x to the 10th plus stuff. So you notice how the degree of the bottom is bigger than the degree of the top. Okay? Whenever you have something like that, you automatically know that your horizontal asymptote is going to be at y is equal to 0. So you're going to have something that looks like this one, the very left-hand side. Okay? Okay. Next one. When the degree of the top is equal to the degree of the bottom, right? You have a horizontal asymptote specifically, right, at y is equal to a divided by b. Okay? And what I'm saying here is you have an f of x value being equal to a x to the n plus, and I don't care what the rest is, divided by b x to the n plus, and doesn't matter what the rest is. So if the powers are the same, right, on the top and the bottom, so if the degrees are the same on top and the bottom, right, you just get to divide those front terms. That's it. Okay? Lastly, if the degree of the top is bigger than the degree on the bottom by 1, okay, you have something called a slant asymptote or an oblique asymptote. Okay, something that has a slant asymptote looks like this. Now, if you've taken pre-calc before, right, the way that you find a slant asymptote is by doing long division with the polynomials. Okay, by doing that, right, you're going to get the equation for that slant asymptote. Okay. I am not going to concentrate on that for this class, so long as you can recognize that, oh, this thing is going to have a slant asymptote, that's enough for me. Okay. If you do want to find out how to find the slant asymptotes, right, it's all spelled out in the textbook. I'll let you read it. Essentially, you're going to be doing the long division. Okay? All right. So, let's do some examples. Okay? So I've got three rational functions here, right? And we're going to do a bunch of stuff. We're going to determine vertical, horizontal, slant asymptotes, or removable discontinuities, and then we're going to describe local and end behavior. Okay? And hopefully, right, our guesses should match up, right? Our guesses should match up to the actual function itself. Okay? And what I'm going to do, and I know it's really hard to say don't use a calculator yet. You'll see that we're going to require it anyway, right? But try to do as much of this without using a calculator as possible. I think the local and end behaviors are, you're going to need the calculator, right? But for the vertical, horizontal, and slant asymptotes, or the removable discontinuities, right? That you can sort of figure out without using the calculator. Okay, so I'm going to do it this way. I'm going to say this one's A, this one's B, and this one's C. Right? Okay, so let's do A first. Okay, so first of all, what I'm going to do is this. I'm going to go g of x. I'm going to just copy it down. 6x cubed minus 10x divided by 2x cubed plus 5x squared. Okay, notice, right, that for this, the degrees are equal, right? So automatically, right, horizontal asymptote at a divided by b. In this case, my a and my b are 6 and 2, so that means I have a horizontal asymptote at 3. Okay? Since the degrees are the same, we know the horizontal asymptote is there, right? There's not much else to do. There's no slant asymptote, right? So now we get to move on to vertical asymptotes. Okay, so what I'm going to do, I'm going to factor this. I'm going to try to factor out as much as possible, right? So from the top, I can do x times 6x squared minus 10 all over. The bottom is going to be x squared 2x plus 5. Okay, from the bottom, right, we can see that x can't be equal to 0 because that makes us divide by 0, right? And then x cannot equal negative 5 over 2. If we plug this in to here, right, that screws stuff up. We're going to be dividing by 0. We can't do that, right? So these two should be our vertical asymptotes. Okay, now I know this is coming out of left field. I know this. You guys see there's an x on the top and then there's two of them on the bottom. So what do we do now? Turns out, right, we might have a hole, right? At x equals 0. Okay, so for now, for this portion of the class, just be able to describe, right? Be able to sort of look at a function and maybe hopefully pick out at least a couple of things, right? Okay. It wouldn't do us any good if we don't test this out, right? So I'm going to go ahead and turn on the very first function, right? There it is. So, whoa. So remember how we guessed, right? That we should have a horizontal asymptote at y equals 3. Do you guys see that a little bit? There we go. So let me squish this down a little more. You guys see the y equals 3 line right there. And if we just keep going that way, you guys see that the function gets closer and closer and closer to that line, but never crosses it. So our horizontal asymptote is good. And then according to the rest, right, we should have vertical asymptotes at 0 and at negative 5 over 2. Okay, and lo and behold, right, 0 has an asymptote. And then 5 over 2, that's going to be what? Negative 2.5, right? So 2.5 should be this line right here. If you take a look, right, our line keeps getting closer and closer and closer to that. So we were able to discern everything that we needed, right, from the function itself. Okay, moving along. B. B is the scary one. I want to say scary in terms of it's one that produces something that, come on, it's one that produces something that really hard to figure out. I just sort of named it, right? And I don't expect you guys to be able to find it. If you do want to go find it, It's in the textbook, okay? So if you take a look at h, right? X squared minus 4x plus 1 all over x plus 2. The degree of the top and the degree of the bottom, they are different. The degree of the top is bigger by 1, right? So this automatically says we have a slant asymptote. I'm not going to make you go find it, okay? You'll see what I mean when we graph it right now. It is going to show itself. It's going to be present, right? But I'm not going to make you guys go find the equation for it, okay? Now, that is the slant asymptote. We know that it's going to have one, okay? For the horizontal asymptote, or sorry, the vertical asymptote, right? We know that it's going to have one at -2. So notice I can't plug in -2 to that because if I do, I divide by 0. Can't do it, right? Okay, so for B, we have gathered, at least for now, that this thing should have a slant asymptote and it should have a vertical asymptote at -2. Okay, back to our handy-dandy Desmos. And that's this one, h of x. Boom. Okay, let me zoom out a little bit. There we go. So you guys notice that our vertical asymptote, let me actually pull this apart a little bit. There we go. We're supposed to have a vertical asymptote at -2. And lo and behold, all right, let me actually squish this a little more. You see that it's starting to hug that x equal -2 line, right? There it is. Okay, and let me zoom this out, or zoom it in a little bit. You guys see that there is a line there. It's slanted, hence why we call it a slant asymptote. There's a line there that it looks like it's getting closer to it, right? But we don't know what that line is, okay? So it turns out that line is this, x minus 6. So notice if I graph the line, right, it really sort of becomes apparent that it's hugging the green line. Our function is hugging this purple line, okay? So like I said, I'm not making a big deal about you all being able to find this line. I do want you to be able to determine whether or not one of these lines exists for a specific function. That's it, okay? Like I said, if you want to go find out how to find it, it's in the textbook. I'm not going to make a big deal about it for this course, okay? Okay, moving along, one more, and that's C. Come on, C. There we go. K of x. X squared plus 4x, all divided by x cubed minus 8. Okay. Well, I'm trying to erase that dot, but it doesn't want to go away. I'll live with it. 8. Okay. So first of all, notice that the degree of the top is smaller than the degree of the bottom. Automatically, from my list from up above, right, we know there's going to be a horizontal asymptote, right, at y is equal to 0. Hands down, we're done. Okay. Now, vertical asymptotes, right, we need to do the bottom is equal to 0. Okay. I'm going to give you guys an equation. Let me see if I can get it right. Yeah, there we go. This should come from high school. We're not going to use it very often, but I think it's often enough so that I should write it down. X cubed minus a cubed. Okay, that is equal to x minus a, x squared plus ax plus a squared. Okay, why did I write this down? Because the bottom for this one, x cubed minus 8, right? I'm going to rewrite the 8 into 2 cubed. So that means I can factor this a little bit. X minus 2, x squared plus 2x plus 4, right? So then that means this bottom, or this whole function, k of x squared plus 4x all over, it can change into that. X minus 2, x squared plus 4x, but plus 2x plus 4. Right? I'm going to do one more bit of factoring the top. I can pull out an x. X plus 4 all over x minus 2, x squared plus 2x plus 4. Okay. This is the best I can do in terms of factoring, right? Notice that nothing cancels, okay? And we already have a horizontal asymptote at y equals 0. Okay, since nothing cancels, right, we don't have a hole. Yay. Okay. But the bottom still can be 0. In particular, this one. Right? If I plug in positive 2 there, I might divide by 0. That leads us toward a vertical asymptote, right, at x equal positive 2. Okay. So one thing I need to note, in order to find vertical asymptotes, right, we need to set the bottom equal to 0. That second portion of the bottom will never equal 0. And the reason why I can make that determination is if you put it into the quadratic equation, right, because we want it equal to 0. If we put it into the quadratic equation, it provides no solution. And if you try to type it out into your calculator, you get an error. Okay? Okay. So we have, for this function, right, we have two things. We have a horizontal asymptote at y equals 0 and a vertical asymptote at x equal positive 2. That's what we should expect, right? There it is. So notice, right, my y values are getting really close to 0 as I go toward the positive values, right? Whoa, whoa. And as I zoom out, we can see that there's a vertical asymptote at x equal positive 2, just like how we had determined, right? Okay. Okay. So like I said, a lot of this class I want to do through Desmos a lot more than by sort of reasoning it out. However, right, I do hope that you guys are able to sort of look at these functions and at least pick out what you should and should not see. Okay? All right, what comes up next? Quick checks. Again, try these out. Okay? Verify using a graphing utility. And then after that is lecture questions. Okay? If there's any questions on the stuff that I just covered, ask me during quick check time. Come down to the math lab or come see me by my office. Okay? Besides that, happy studying.